What specific problem does MolmoAct aim to solve, and how does it address the limitations seen in current vision language action models?
MolmoAct aims to solve the problem of limited flexibility and robustness in current vision language action (VLA) models, which struggle with task transfer, scene adaptation, and providing explainable decision-making. It addresses these limitations by integrating a structured reasoning pipeline that incorporates depth perception and visual reasoning traces, enabling the model to generate spatially grounded action sequences. Unlike existing VLAs that primarily rely on high-level language instructions, MolmoAct employs a three-stage reasoning architecture that first encodes depth-aware perception tokens, then generates mid-level planning representations, and finally predicts precise low-level robot actions. This structured approach not only enhances the model's performance on standard benchmarks, but also allows for explainable and steerable behavior, making it more adaptable to novel tasks and environments. By focusing on embodied interaction and fine-grained data, MolmoAct effectively bridges the gap between perception and purposeful action in robotics.
How does the proposed method work? Illustrate step by step the three-stage reasoning architecture utilized by MolmoAct.
MolmoAct employs a three-stage reasoning architecture to facilitate action reasoning in robotics. First, it encodes observations and language instructions into structured 2.5D representations by generating depth-aware perception tokens through autoregressive prediction. This step enhances the model's spatial understanding, which is crucial for accurate robot control. Next, these depth tokens condition the generation of mid-level planning representations, visualized as trajectory lines in image space, which outline the intended motion of the robot's end effector. Finally, the model predicts precise low-level robot actions based on the generated trajectory lines, ensuring that the actions are grounded in both the inferred depth and the planned motion sketch. This structured approach not only improves performance, but also enhances explainability and steerability of the robot's actions.
Can you walk through a simple example of how MolmoAct processes an input to generate an action, detailing each stage of the action reasoning procedure?
MolmoAct processes an input through a structured three-stage action reasoning procedure. First, given an RGB image observation and a language instruction, the model autoregressively generates depth perception tokens that summarize the depth information of the scene. Next, it produces a visual reasoning trace, which is a polyline representing the planned trajectory of the robot's end effector, ensuring that the motion is grounded in the spatial context of the image. Finally, based on the generated depth tokens and visual reasoning trace, MolmoAct predicts the action tokens that correspond to the robot's next control step. This sequence of generating depth perception tokens, visual reasoning traces, and action tokens allows MolmoAct to execute actions that are both spatially grounded and contextually relevant, enhancing its performance in robotic manipulation tasks.
What are the key advantages of using MolmoAct over existing robotics methods, particularly in terms of efficiency, explainability, and adaptability?
MolmoAct offers several key advantages over existing robotics methods, particularly in efficiency, explainability, and adaptability. Firstly, it achieves significant efficiency in training, requiring only 9,216 GPU hours for pre-training, which is 4 times less compute than the GR00TN1 model, while still delivering strong performance on benchmarks like Libero and simpler ENV. Secondly, MolmoAct enhances explainability through its structured reasoning pipeline, which includes depth perception tokens and visual reasoning traces, allowing users to visualize and understand the decision-making process behind robot actions. This contrasts with traditional models that often lack transparency in their action selection. Lastly, MolmoAct demonstrates superior adaptability, effectively generalizing to novel tasks and environments with lightweight fine-tuning, outperforming other baselines in both simulation and real-world settings, thus proving its robustness across diverse scenarios.
How was MolmoAct validated or tested? Please detail the experimental design, datasets used, and the metrics employed to demonstrate its effectiveness.
MolmoAct was validated through a comprehensive experimental evaluation that included both simulation and real-world settings. The model was tested on standard benchmarks such as Simpler ENV and Libero, where it was compared against strong baselines like GR00TN1, 1 and Trace VLA. The datasets used for training and evaluation included a mixture of action reasoning data from the OpenX embodiment, AUX, dataset, auxiliary robot data, and the newly curated MolmoAct dataset, which contains 10,689 trajectories of a Franca robot performing various manipulation tasks. Performance metrics included accuracy rates on visual matching tasks, task progression metrics in real-world scenarios, and ELO ratings from human evaluations for instruction-following tasks. The results demonstrated that MolmoAct achieved strong zero-shot performance, effective adaptability through fine-tuning, and superior generalization capabilities, outperforming its competitors across multiple evaluation axes.
What limitations or drawbacks of MolmoAct have you identified, and how might these impact its application in real-world scenarios?
While MolmoAct demonstrates significant advancements in action reasoning and spatial understanding, it still faces limitations that could impact its real-world application. One notable drawback is its reliance on depth perception tokens, which, while enhancing spatial reasoning, may not fully account for the complexities of dynamic environments where depth information can change rapidly. Additionally, the model's performance can be influenced by the quality and diversity of the training datasets. If the datasets do not encompass a wide range of real-world scenarios, MolmoAct may struggle with generalization in unfamiliar contexts. Furthermore, although the model allows for visual reasoning trace steering, this method may not always be intuitive for users, particularly in complex tasks where precise control is required. Lastly, the model's explainability, while improved, may still leave gaps in understanding the decision-making process, which could hinder trust and reliability in critical applications. These limitations suggest that while MolmoAct is a powerful tool, careful consideration and further refinement are necessary for effective deployment in diverse real-world settings.